Well, hello everyone. My name is John, and I want to welcome you to this exciting 1-hour session where we're going to talk about the exciting world of how computers actually can effectively communicate with each other. And in today's age, with everyone needing computers, every industry, and to me, this is a fascinating aspect. And so with that, this is going to be an excerpt from some of the CompTIA Network Plus concepts on there. So I definitely want to welcome you. Again, feel free to ask any kind of questions. Actually, the chat window, I guess, is the best preference on that. But I always encourage questions because I like to answer questions. In fact, I like to ask questions, make sure people are understanding things as well as we go, too. Very important. I apologize for that. And so with that, one of the things I do need is I do use my pen. I do a lot of drawing on there for explaining things. All right. So with that, always like to kind of get an idea first. Is anyone brand new to IP addressing? Is like, what is that? It's like a whole new out of this world thing. Anyone kind of fall into that kind of category? Just kind of curious. Just one of the things I like to do is kind of get in, introduce, the students, see kind of what level of knowledge they have as well too. So anyway, so again, so if anything we cover, if you need me to reiterate or go back, please feel free. This is actually very exciting, and we even have some handouts and things that you've seen, and I'll be going back over that there to help better understand. So after, for the takeaway, you can look at it and digest it and really understand it, because IP addressing or logical addressing is a concept that does take a while to really truly grasp. I know it took me a while too. So with that, first thing is being an excerpt from CompTIA's Network Plus things. We have a collection of slides for that. And so the first thing, when it comes to computers, the main purpose of any network is to share resource, to communicate with one computer or one device to another device, whether to get out to the internet or upload, download a file, or anything. And so and with networks, there's always a structured approach. And so there's many different standards out there for the networks. And one of these to help understand what happens down at the electron level. Because remember, it's just circuitry moving back and forth, little voltages, bits of ones and zeros. So that's the language of computers, is binary. And so with that, they came up with a way of explaining. It's not a standard. It's just a way of explaining what happens from one computer to another. And it's called the OSI 7-layer reference model, or Open Systems Interconnection. Now with this, you have 7 layers, and each layer performs a specific function to get the data ready to be sent across on the network to be received. So you, the receiver, can process whatever request that is. And so with that, with these 7 layers, let's say I want to bring up a web page, right? So I bring up my browser and I type in the address. Well, that application, whether it's a web browser or my email program, whatever, that is going to request a network service. So they contact the application layer. So based on the various protocols that are used, like HTTP or or SMTP if it's email, is going to be requesting network services. Then it is passed down to the presentation layer, which starts reformatting the data into a more usable structure. Then they hand it down to the session layer, layer 5, and the session layer acts as like the supervisor, the person in charge to say, okay, transport layer, you need to establish connection with another computer. You need to maintain this connection. Okay, now you can sever connection. Right? So they're the boss. Now the transport layer, what they do is first thing they do is they take the data. Say if you have a 10 gigabyte file, well, it's just too big to go across the network. It's not structured right. And so the transport layer starts breaking down the data into smaller bite-sized chunks, right? And then it's called encapsulation. Each layer adds additional bit of data, right? Now, since all these little bytes of data are going to go individually across the network, the transport layer adds a sequence number. So that way, when you receive these, you might receive them out of sequence, so you can put them back together in the right order. Okay, with that, and they also assign a logical port number because each network service requires a certain port to listen in for that type of request. For example, HTTP uses port 80. Email has various ports like port 25 or port 110 or 993 type thing. So transport layer adds a port number. Now they hand it down to the network layer. The network layer, this is where they add the source and destination IP address. Just like mailing a letter, you have to properly structure the destination address, and then you have your return address, and you have a stamp. You just can't put anything anywhere you want to. You have to put it in a proper spot, right? So the network layer adds the source and destination address. They hand it down to the data link layer. At the data link layer, this is where local addressing is performed. You also have what's called a MAC address or local address, media access control address. That is also added into the little data packet. And then the physical layer, by this time, it's just a voltage, it's ones and zeros, and it's put on the media, whether it's a cable or wireless. So when I do sending the data is reversed when you receive it, right? And so the whole thing, the main purpose of these layers is to do data encapsulation. Each layer adds a little bit of information into the data packet. Sorry about that. I thought I turned on. All right. And so what you have when data is going across the network in the proper structure, you have what's called a data packet, right? And the basic structure of that, you have three elements, right? You have the header. The header would be addressing information. There's a whole bunch of extra information that we'll be covering of how to get it from me to you, right? That'd be like the information on the outside of an envelope. Then the data would be the contents of inside the envelope, the data that you're requesting. And then you have a footer, which is a checksum, which allows for data integrity to make sure the data hasn't been corrupted in transit or something like that. So three major elements, right? And so first we have to do the data encapsulation, and it provides the addressing. So it can be sent across the network because there's many other devices. Remember, we're not connected directly with a cable between you and I. We have all sorts of other network devices. We have switches and routers, firewalls, proxy servers, like, oh my, So we need to provide proper addressing. Now, when you have communication, you really have two categories. You have local communication. Like if you're sitting right next to me, we're on the same local network. So we communicate using the same basic layer on these. If you're long distance, then I would need additional other layers to properly send it to you. And so again, the generic term for the whole data packet is called a protocol data unit, because there's different network protocols that are used. And nowadays, primarily the main protocol is called TCP/IP, Transmission Control Protocol, Internet Protocol. But there are others. But the protocol is a way of it's a common language. So that way Windows can talk to Apple, and Apple can talk to Linux, all sorts of things. So it's properly structuring of the data. And so when I send it, I add additional data. When you receive it, you decapsulate, you remove that additional data because it's no longer needed, right? And we do this for the entire connection that you and I are talking. It's pretty fascinating. So it works. Now, when it comes to, again, matching the 7 layers with the various network devices, right? Because you have a workstation, or it could be a server, typical computer, but you also have switches and routers and firewalls and things. And so each of these different devices and the functionality operates at different layers, right? So like, for example, you have down at the very bottom is the physical layer. This it's your media, whether wired or wireless. And so at the physical layer, there is no logical intelligence. There's no real processing. It's just moving the data around. It's just bits of 1 to 0. Right? Then at the data link layer, what you have is your network adapter or network interface card, whatever you want to call it on there. This allows you to connect to any network. Right? And so that layer 1 and layer 2 operate at your network adapter card. Right? Also, we see some of the devices that we run into in a typical network. We would have, of course, the transceiver. Basically means it's a way to transmit and receive information, send it and receive it on your network adapter. So you have your cabling, or it could be a wireless access point, it could be a wireless network. Media converters, what they do is they just transfer from one media type to another, like from copper wire to fiber optics, or from wire to wireless, back and forth. And then a hub is a way to easily connect multiple computers together, but there's no intelligence. Everyone hears the same information with it. It's like a big party line. Now, with the data link layer, to improve communication, better performance and things, they have a bridge as a precursor to a switch. The bridge and the switch, what they do is they use, again, the MAC address, media access control address, to look for the local addressing. Do I need to send it long distance, or can I just send it directly to whoever's plugged in to me on there? And so these are devices that operate at the data link layer. Now, what's interesting, the information of how the proper structuring of that data packet is technically called a frame. Called a frame. Then as we move up the network layer, this is where IP, Internet Protocol, operates. And so the biggest devices here, we have routers. Routers are designed to look at IP addressing for long distance forwarding of traffic, ultimately to the destination. Basic firewall, packet filtering firewalls. They can, a firewall is mainly to prevent any unauthorized entry or exit through that device, better for protection of your network. Now at this time, instead of a frame, it's now that same data packet is called a datagram. Ooh, change name. Now at the transport layer, when I start breaking things up into smaller chunks, the same thing is now called a segment. Right? Now, so again, they have different names for things. Now you can easily use these terms, or you can just call it a data packet, or whatever you'd like to, because you want to be on the same language, when people interact with each other. Now, excuse me, the top 3 layers, these are all more what they call higher level functional type protocols and services. So depending on what I'm using, whether I'm using my web browser to access a web server, or my email or SharePoint server or something, that the 3 top layers work to make the application interact with the network service. So this here's a kind of a neat little design, because again, when the main purpose of why a lot of people take our classes is they like IT, but what's the main purpose of IT? To keep the network running, make sure everything is available to our customers at acceptable levels of service, right? So troubleshooting is a big thing, because my philosophy is always tell my students, how can you troubleshoot and manage your network if you don't know how things actually function? You have to look at the symptoms, so it's kind of interesting. So this is just a neat little way of what actually transpires down at the electron level. Now, when it comes to IP address, again, a datagram, right? Now, within the 3 sections of the datagram, remember, you have that little data packet here, you have your header, right? You have your header, and that's kind of what we're kind of discussing right now, right? So inside the header is a lot of good forwarded information that are used by other devices, right? So with that, for example, you have the version, right? Is this IP version 4? Is IP version 6? The header length is how many bits the header is. For example, differentiated services is used at layer 3, the network layer, to help prioritize different types of traffic. So that way we can process other data faster. Like, for example, real-time data like voice over IP or stream video is processed or has a higher priority than, say, standard email, for example. The total length is the entire length of the packet. Identification flags and fragment offsets are used by the other devices when they're communicating to establish connections and negotiate with each other to let us know what kind of data is this. Is this a beginning packet to establish a connection, or is this a type of packet to start closing down our connection and so forth? A time to live. when you have a datagram that as it gets put on the network, as it gets forwarding around from all of one device to another, this value decreases by a value of 1. So what happens if you're too far away, that when we reach TTL of 0, this packet is no longer able to be forwarded and it gets dropped. Because without a time to live, there are times when data will not ever reach the destination. It's just floating around in cyberspace around the internet, never going anywhere. And we don't want to live on forever. Pretty ingenious there. The protocols, what kind of protocols? It's TCP, UDP, ICMP, IGMP type of thing. And then the checksum is a way of validating the integrity of the header information. Again, then you have your source and destination IP address, and then any additional other information. Now, again, this is just only used by the network layer. Also, don't forget you have the MAC address of source destination, which is used by the data link layer. So there is a lot of good detailed information in this. And so when it comes to addressing, what is the mystique about it? Well, we're mainly going to talk about IP version 4, right? And so IP version 4, it has been around a very long time, right? And so it consists of a, say, 32-bit binary word, which is the language of computers, right? Humans don't like binary, right? It's just too complicated. And so out of a 32-bit word, what they've done is they broke it up into 4 groups of 8 bits each, called an octet, right? And so another term for 8 bits is a byte, B-Y-T-E, okay? And so what they do is they use dots to separate these octets. And then to make it easier for us humans to understand what we're doing here, they convert it binary into decimal base 10. So these is called the whole thing dotted decimal. So when you're a technician and you're looking up for troubleshooting or configuring, design a network, whatever, what we see, for example, is 198.51.100.1. Much easier for humans to understand. They're like, yay, right? Now, of course, the next thing, before we can go a little bit farther, we need to understand, well, how do we count in binary? You know, this is always very vague for some. And so in my typical classes, what we cover here in this 1 hour, I usually spend about a good 2.5 hours covering this really in depth, because my main concern is to make sure my students actually understand the material, because it's their job, you know, when they go back to work, to manage their IT. It's not just to take a test. I mean, it's good, but they need to be able to know how to do their job better, right? So I really love being able to do this. And so when it comes to counting in binary, now, just to kind of be curious, anyone here unfamiliar with binary? Just kind of curious, just like to kind of get an idea, because I always ask anyone brand new to binary. I'm curious. But I usually get a couple people. It's like, yeah, I'm new to the IT world and I don't know anything about this stuff, you know, so, which is good, but it's challenging, but it's good. Okay, so with that, let's talk about how to count in binary. Okay, and again, now what I do in class, I kind of give them a reference. So I start off with decimal, right? Because everyone's learned how, you know, decimal from kindergarten, you know, from 0 to 9 and you know, everything. And so with that, we have a representation of, say, 1 octet. So we have 8 placeholders. So I got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1 octet. Now with base 10 decimal, you have any digit between 0 and 9. And so with that, I just start off, say, okay, easily just use the number 1, right? So when you put the value 1 right there, so based on the placeholder where it is from the decimal point. And as we know from kindergarten, that placeholder, this equals a decimal value of 1. Yeah. Now what happens if we set this to a 0 and move it 1 placeholder over? Well, being decimal, it increases the factor by 10. So now this is a decimal value of 10, right? And we do it again, and there's a value of 100, right? So, you know, so basic structure is the same no matter what numbering system you use, right? Okay, so now with that, let me clean this up. Now in binary, we only can use ones or zero, on, off, true, false, yes, no. So the placeholder is really the most significant aspect of it now. And so now if we place a 1 right there, this would be a decimal value of, well, 1. Now in binary, if we move the placeholder over 1, because it's binary, the value doubles. So this by being 1, 0, this would be a decimal value of 2. And we do it again. And we just move a 1 placeholder over, it'd be a decimal value of 4. Right? And we can see, this would be 8, this would be 16, 32, 64, and 128. Okay. So if we had a single bit set in that placeholder, that would be the decimal equivalent of it. Now, when you have values, here, because you're going to have usually a variety of ones and zeros, in an octet. So when you have, let's say, for example, you got 1, 1, 0, 0, 0, 0, 1, 0. Let's see, something. Well, all you have to do is simple addition. Let's say, okay, well, we'll take 128 plus 64 plus 192 plus 2, 194. You just add up the places that are set to 1, ignoring the ones that are 0. And so we can have any number for octet can be anywhere between, if they're all zeros, to be 0 to 255, which is 128 plus 64 plus 32 plus 16, so forth. Any number in there is a valid number in an octet of an IP address. And so what we do, kind of clear this out now, is that for an IP address, we can have any range between 0.0.0.0 to 255.255.255.255, any number combination. And so here's another example. Say, here's our binary value at 11000110. All we have to do is do addition. The ones that are set to a 1, so we just take 128 plus 64. Oh, 192 plus 4, 196 plus 2, 198. Right. So it's just simple addition. And now when it comes to converting from decimal into binary, now that can be a little challenge. When people first see like, oh, I need the Windows calculator or something. No, we don't. The way I do this, kind of clean this up here, is if you think of the game show, The Price is Right. Right, you're a contestant on The Price is Right, and you have to bid up to without going over the value of that prize, right? It's the same thing here. So here we have a value of 51. Say, okay, what is it in binary? Well, we see that 51 is less than 128, so that's a 0. 51 is less than 64, so that's a 0. Okay, so we said, oh, 31, 32, well, that can be set. So we just take 51. Well, you just take 51 minus 32, right? And they say, and I think that's be 8, be like 18. I said, okay, well, 16, right? So we say, okay, so that, it was 18 minus 2, right? Or should be 3. That's 15. Then we do, okay, 8's too big, 4's too big. So we got 2 and 1. So that's all it is. Think of The Price is Right. One of the easiest ways. Because remember, I always tell my students, I don't live and breathe computer stuff. I had to really study and learn this because I want to be the best instructor possible to make sure my students understand the material. Because there's a whole wide world out there of different aspects of IT. And this is just a building block functional component of that. So pretty interesting, how to convert from binary to decimal, decimal to binary. Okay, now when you have an IP address, 32-bit binary with 4 different octets. Now with that, an IP address is worthless to a computer. Computers are very stupid. They don't know anything, right? So the IP address, an IP address would be like a street address, okay? But if you put just 123 Main Street on an envelope, the Postal Service can't deliver that. It needs a city, state, and zip. So one element is the computer. Your computer needs to know, well, what network do I actually belong to, right? Basically, what's my zip code, right? And to do that, you also have a 32-bit binary word called a network mask. And a network mask, its purpose is to reveal the network ID portion of the IP address, hiding what they call the host ID. Because you have two parts, network ID and a host ID. So, so here's an example of a network mask. With that is a continuous string of ones, and then a continuous string of zeros. Always in that format. And so you can have any combination of ones and zeros, right? But they have to be continuous, right? So what happens? Your computer performs an ANDing function. It compares the first bit of the IP address with the first bit of the network mask. ANDing will only produce a 1 if both values are a 1. So what happens with the first 3 octets, it's an identical mirror of the first octets of the IP address. So that will identify the network ID portion. Since the last portion is zeros, it ends up with 0. So I was like, well, that must be for the host, and that's not part of my network. So that's the function that it does. So in other words, the computer says, oh, I belong to 198.51.100. Okay, that's always the first thing. Now, one way to help make life easier for IT technicians communicating with each other, they use a slash notation, right? So like if you and I are corresponding with each other, you might say, well, what's my IP address, blah, blah, blah. I would give you 198.51.100.1, but then I would do a slash 24, because that tells me how many bits of my network mask are set to a 1. Oh, really neat little shortcut. And so since you can have a variety of different bits set to a 1 for a network mask, one of the things that we have for slash notation, if the first 8 bits was my network ID, so it'd be 255.0.0.0, this would indicate a /8. If it was 255.255.0.0, there would be a /16, and then a /24. So that's where they come up with that slash notation. Now, what they've done when they talk about default masks, they're referring to what's called classful IP addressing. And what they do is, okay, to make it easier for technicians, they're going to say, for the network ID, we're going to take the first complete octet, and that's called a class A network. The first 2 octets would be classified as a class B network. And the first 3 octets being used for your network ID would be a class C, right? This is where they come up with this. Now, with that reference guide, because I'm going to be referring to that, so you already had a chance to download it here. Now, with this, I made this for my students because I understand. I was in their shoes. I said, how do I explain it? How do I, So it's really 2 columns of information. So here's an example of what an IP address would be in dotted decimal. This is what the computer would see. We'll get to hexadecimal notation here in a minute. But here's your 8 bits and the value of the placeholder. Now, these numbers, these would be used for like network masks, because since it's a continuous string of ones, we need to be familiar with these numbers. Like, so if the first bit was only set for the network ID, of course, it always is 128. If we always have the first 2 bits set, be 128 plus 64, it'll always be 192. And then 224 for the first 3 bits, 240, 248, 252, 254, and 255. Now, you might sometimes see this type of numbering where you have 2 means it's binary, and then the superscript value indicates the placeholder, where the bit would be set. And in computers, the very first placeholder is always 0. And so it sometimes can be a little confusing for people. So I show them this, but when it comes to people understanding it, it's all up to them of how are they best to understand it. Now, here's, for example, for classful addressing. So a class A would have the network mask 255.0.0.0. So the very first octet is always the network ID. So it means we have 3 octets for host IDs. Class B would be 255.255.0.0. A class C would be 255.255.255.0. Now there are also a class D and E addressing, but we can't assign these to people, computers on our network. Class D is for multicasting, for communicating with a group of computers, not everybody. And E is for experimental use, but we can't assign those. Right? So these are the class full aspects. Okay, and I'll be coming back to this. So understanding the basic structure is half the battle. Right? So knowing the network ID portion. Now, the next thing is this here can be a little throwing a wrench at the monkey, or is it throw a monkey at the wrench? I'm not sure what to do. Anyway, they collect. You also have the ability to customize and design your network how you see fit. So here's an example. We start off with a classful ID of 192.151.100.0, which is our network ID. But then we decided, well, we don't want to have one big group of computers that's like a big party. No, they can't hear, performance degraded and things. So they said, hey, let's subdivide or borrow bits from the host ID and add them to our network ID. Then that is called subnetting, making smaller and smaller groups of computers. Right? Now, a little concept of this is, let's say, for example, you have like 1,000 computers. It'd be like one big party. People can't hear each other, too much noise. So for better performance, we decided to design our network and say we're going to have 5 groups of 200 computers. Right? Now, what you do is you group similar computers together. Like servers here, HR computers, sales computers, whatever. And so since they're all similar computers, they can freely communicate directly with each other, right? And this is called a subnet, right? So if we go back to the standard class full addressing, again, let's say we got 192.168.0.0, that's our original. Well, this one could be 0.0, this could be 1.0, this could be 2.0, this could be 3.0, and this could be like 4.0. So there are 5 separate different networks, different network IDs. And so by doing that, these the 200 computers are not interfering with communication with others. Dramatically improves the performance of your network, right? That's a purpose of this subnetting. So now take it another little step farther. Here we see we have 8 bits for host ID, but we decided to borrow 4 of the bits. So what do? In our network mask, we take the 4 bits that were originally zeros and we convert them to ones, adding them to our network ID. Right? So we still leaves 4 bits for our host IDs, right? Now, by doing this, when you subnet, what you're doing is you're taking your network and you can't have as many computers in a group, right? Because remember, if you have 8 bits, you can only go up to 255. But if we now have half of that, we only can have 126 computers, or maybe 62 computer, whatever we design it to be, that can be all together in one simple little local network. And so there's a dividing line between, when you design your network, how many computers do I need to be on a local network, versus how many separate networks do I need? And this is all part of the designing aspect. And so usually the level of coverage that when I cover this is designed to help my students be part of the team members, not to be the engineer to come up and write this up from scratch, to help them understand the terminology and the concepts of what actually is happening. Okay, so now since we borrowed additional 4 bits for our network ID, we no longer are /24, we now have to be a /28. Yeah. So we only have 4 little bits on that. So now with that, let me clean this up here. When it comes to, for example, now we have 4 bits, right? Now let's go back to our document here. We're kind of taking a pause. Let's go to hexadecimal numbering system. In hexadecimal, this is called base 16, right? And so with hexadecimal, we can now, a single hexadecimal value represents 4 binary bits. So in hex, we have 0, just like kind of in decimal, 0 through 9. But then we go A to F, because then after F, it'll have 10, so it's base 16. So out of these 4 bits, we can have any combination between 0, 0, 0, 0, and 1, 1, 1, 1. Right? And so where we use hexadecimal notation is to display MAC addresses and IP version 6 address, because IP version 6 is a 128-bit address scheme. So dotted decimal would be really confusing. So we use basically hexadecimal. And with that, we have 4 hexadecimal values, and we separate it each group by a colon, right? And since there's only 4 hexadecimal values, it's called a quartet instead of an octet, right? So it's much easier to display binary, converting each digit, like 2 would be 0010, A would be 1010, and it just kind of strings it all out. So that's where we use hexadecimal. Now, one of the things that's interesting, as we see here, since IP version 4 is only 32 bits long, that we've actually ran out of available IP address, because you have 2 types. If you want to get out to the internet, you have a public IP address, fully routable, and but you have to pay for this, usually through your ISP. And so what they've done is that, okay, people don't have that kind of money. So what we'll do is we'll designate certain ranges to be considered private, which means they're free, right? You can use them any way you want to, but you don't have to pay for it, but you can't route to the outside world. You can route within your internal network, but that's it. So for the class A, the 10, the first octet, anything for network ID of 10 is free, is private. Now for class B, it's a little different. Yeah, because it's 255.255.0.0. You have anywhere between 172.16 all the way through 172.31. Any combination there. Now for class C, the first 3 octets is the network ID. Anything that's 192.168. Right? Doesn't matter what the other 2 are, whatever you want it to be. Right? And so this really saves a lot of money for companies. And that's why a lot of times people say, well, I see 192, 168 all the time. Wouldn't there be a conflict? We can't have 2 people living at 123 Main Street. Well, because these are private addresses, they will never interfere with each other, because you're on your network, I'm on my network, right? Because we have to communicate with public IP. So this is actually a stopgap measure, because that's why they came out with IP version 6, right? So, but when it comes to understanding the basic concepts of any logical addressing, IP version 4 is always at the top of the list, because once you get that, learning IP version 6 is much easier. So that's why I made this as a little study guide on things. Now remember, when we went back and we say borrowed bits have a subnet mask, here's a simple example. We take a standard class C, right? We have a standard class C, but we said, hey, we need to take our network and cut it in half. So we borrow a single bit, convert it from a 0 to a 1. And so now our new network mask would be 255.255.255.128. So here's our parent network ID. So the first 3 octets, they don't change. Since we have a single bit and there's only 2 states, 0 or 1, it gives us 2 separate networks. Now for the IP address, so for example, up here, that value in binary, the first bit would always have to stay 0. So like, how many hosts can I have in a particular network? So the first bit of 128 has to stay 0, but the others can be anything between 1s and 0s. So that means we have 7 bits left over for host ID. So we can be anywhere between 00001 to 1111110. right? Now we can't have this bit set to a 1 because that would be all the host bits set to a 1, and that's the local broadcast address. So that means that we only have 7 bits for hosts. We can only have between IP address between 1 and 126. Now for the other subnet, the first bit has to stay 1. The 128 bit has to stay 1. So we still have the last 7 bits for the host IDs. And so, but we have to add all 8 bits in the octet. So we get 128 plus 1. The first available IP would be 129. And then we add them all up. We can't have the last bit set because that'd be the broadcast address. So we have up to 254. Right? As one example. Now, here's just another example where you can borrow another bit, convert it from a 0 to a 1. Now, since we have 2 bits, we can have any value between 0, 0, 0, 1, 1, 0, and 1, 1. So now we have 4 possible subnets that we could use. Yeah, okay. Very cool. So, and so with that, the same principle applies. Now we have 2 bits for the network ID. So now we only have 6 bits for the host. And so by doing that, it halves the number of computers for that local subnet. So now we will only be up to 62 computers. Right? Instead of one big 255 or 254, and then 128 or 126, and then 62. So it gets smaller and smaller, but it has less and less communication conflict between the various computers from one network and another. Okay, so that's kind of what the little study sheet is. So now, once we figure out the network portion, we say, okay, now let's take a look at the host bits, right? So in a typical class C, we have 8 bits, the last octet. And again, we can go anywhere between really, 0 to 255. But for IP version 4, there's certain IP addresses that just cannot be used. So the host bits cannot all be zeros. That would indicate the network ID. We can't have 255 because that would be the local broadcast address. I want to talk to everybody, right? So that gives us between 1 and 254. And so so this is where the pickle comes in. If we start subnetting farther down, we each have a separate subnet. Like here we have /28, so we borrow the first 4 bits. That with that, the usable IP addresses, we only have between 1 and 14. Because we can't be 0, we can't be all 1s, it would be 15. That'd be all the bits, that'd be the local broadcast address. Right? And so forth. So one of the things, IP version 4 is pretty wasteful when it comes to, when you subnet, but it's dual. That's all part of the designing your network to meet your company's needs. So with IP addressing, it operates at the layer 3, the network layer, and it's called a datagram. So you have the header, which is for forwarding information. Biggest thing is source destination address, so I know who I am and who I'm sending it to. The format we looked at is 32-bit binary word, and you have a network portion, a network ID and a host ID. But we need to have a network mask to identify what portion is our local network. We can further subdivide our network by using subnet masking by borrowing whatever bits that we want. And then we looked at our host to say, okay, well, how many available bits do I have determines how many computers I can have in that local network. Right? And the biggest thing, again, it's an introduction to the designing of a network. Right? And as you can see, sometimes, when we get people that like, what did you just talk about? Usually that this is one of the areas that always has to be reviewed and studied and digested for probably the longest aspect of understanding networks, because a lot of times people can grasp the idea of switches and routers and firewalls and cables and things, but it's the concept of IP addressing that can throw them for a loop. Right? So with that, we have a couple of questions we want to see, get you familiar with things. So it says convert the binary value of 11110010 into decimal. What do you think? Feel free to blurt out whatever answer you think it might be. Now you can also use your Windows calculator if you want to, because if you bring up Windows calculator and you change the view to, I think it's scientific or something, you can type in the binary, convert it to decimal. It's not cheating, it's utilizing your resources. What do you think? Right. Again, just think of the price is right. Add it all up. Yeah. So he said, okay, it must be 242, right? That's all it is. Just add them up, 128 plus 64 plus 32, and so forth. Now, convert the decimal value to 72 into binary. Oh, no. What that represents? Right, but you forgot the leading on that. So we remember, like the price is right, 128 is too big, so that first bit has to be 0. Then it would be 1 because 64. So it would be 0, 1, 0, 0, 1, 0, 0, 0. And again, just think the price is right. Say, okay, just doing simple subtraction, and you'll never get it. Now, what is the dotted decimal representation? Using like 255.255, whatever. If you have 8-bit net mask. So with that, the first 8 bits is the network ID. How would that be represented in dotted decimal? Anybody? Remember, we have a class A, a B, or a C. So it'd be like 255.0.0.0 or 255.255. So here, the first 8 bits is it. Very good. It'd be 255.0.0.0. The first octet is the network ID. That's all it is. Remember, you have an 8-bit, /8, or /16, or /24 for class A, a B, or a C. Okay, now, what is the dotted decimal representation of an 18-bit net mask? So here, if we take a look at our placeholders, we got 1, 2, 3, 5, 6, 7, 8 dot. 1, 2, 3, 4, 5, 6, 7, 8 dot. 1, 2, 3, 4, 5, 6, 7, 8 dot. And 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we just got done that this would be a /8. Okay. So then this would be a /16. So all these bits would be set to 1. All right. Now, but they want 18 bits. So now these 2 bits have been added. So these are all zeros, right? Okay. So now we added 2 bits to our network ID. So we borrow the first 2 bits of the third octet. Very good. We just do addition. 128 plus 64, right? Becomes 255.255.192.0. Awesome. Now, with that, given that we have an 18-bit mask like this, are the IP addresses of 172.16.1.10 and 172.16.54.10 on the same network? What do you think? Now, one way, kind of handy way of doing this, we know the first 2 octets are identical. Well, so we don't need those. We don't need those because they're identical. Okay, so really it's only the third octet that's in question, right? That's it. That's the only thing we have to worry about. Now, another thing to help you on this. We go back 18-bit mask. We have 2 bits right here. We know it's 192 for the 3rd octet. Well, 192, that would be like a dividing line, right? So we see that the 3rd octets between 1 and 54. So get back. No cheating. Is that both numbers are less than 192, right? That should be another clue. So what do you think now? Are they on the same network or not? Yes, they are. They're both on the same local network because they're both under 192. Yeah. And in fact, you could have between 1 and 190 would be on the same network, because then you'd have 190, you'd be 192 to 255 would be on the network. So easy, you just look and see, okay, well, these numbers are identical. Get rid of them. Let me focus on, the 1 octet that's in question. Now, if the network mask ID is 10.1.10.0/22, now how many IP addresses are available for the allocation to the hosts? So now, in something like this, right, we're looking at, so what we do, we don't have to care about the IP address. We're looking at the slash notation. So we got 22, right? So now we have 1, 2, 3, 6, 7, 8, right? 1, 2, 6, 7, 8. Yeah, I got 1, 2, 3, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we know that this is a /24, right? We already know. But now they go /22. So that means these 2 bits are been converted from a 1 to a 0. So by doing this, we've added more bits to the host. And so by doing here, we know by default, this equals, we know 1 to 254, right? But now we got 2 additional bits. God. And then in the nature of counting a binary, remember, every time you move one placeholder over, it doubles the value, right? So now these are all 1s, right? We took away 2 of the bits, added them to be more network or more host IDs. Okay, so let's take a look at that. Okay. So now this is actually pretty interesting, because sometimes people think, oh yeah, that's right, because we know this placeholder, right, is 128. Okay, we know that that's that 1 bit. And again, if we double, this placeholder would be 256. This placeholder would be 512, right? But we can't just say, oh, 512, right? Because what about all these other bits? We have to have them all set to a 1. So an easy way to work on this, we say, okay, since again, with the available bits, we can go basically all 0s or all 1s. Easiest way to do this, you go to the next bit, the first bit that's set to a 1, this would be 1024, right? Double. But since we know we want all the bits to be between 0 and all 1s, easy way to do math is we just need to minus the bits we cannot use. Remember, the host bits cannot be all 0s and they can't be all 1. So we take 124, which is the first bit that's set to a 1, minus 2. You kind of getting with me on this? Well, it's a simple addition here of available valid IP addresses. So we could have 1,022 available computers in one local network. Because all these bits would have to be set to a 1, or minus the 1 and the other, right? And that's what the minus 2 is. To say what is the number of available IP addresses, we take, say, how many bits do we got? Minus 2. Right? So that is kind of what this question leads you to. And again, a lot of times technicians, they don't do this every day. So even the best technicians have to kind of refresh themselves a little bit too. So that's basically what they do. Say, okay, just count, okay, so 1,024, okay, minus 2. So it'll be 1,022. Yep. All you have to do, simple addition, just doubling the value. See what you get. Now, again, we have to realize we can't have the host bits of all zeros, and they can't be all ones. That's where the -2 comes in. Now, hopefully, we're able to shed some light on that for you, because as an instructor, I really enjoy seeing people's expression. I think I'm getting to understand this. A little light bulbs coming on. Might be a little fuzzy, but people really enjoyed learning something new. I know I do. That's why I like watching the History Channel thing, right? So veterans starting to understand it. Now, once they start grasping this, again, it may take a while to thoroughly go through it, a couple of months, but see the light sparkle in their eye. And so the thrill of that accomplishment, they shared it. Dude, I just learned this. I woke up in the middle of the night and I understand it now. Whoa, that is exhilarating. I love it, because I want to make people make their life easier by understanding some of these harder concepts to grasp. Now, also, the more they understand about IT, the better they can be confident in their career. Their career path is out in front of them. They can do anything. It can be programming or network security or database design on that. It's just slowly building their knowledge, building relationships with others, cooperating, collaborating with their customers, providing good value services. It's that job well done. That's slowly but surely. And so with that there's a basic excerpt of how we do things. Again, normally I spend about 2.5 hours covering this. Hopefully you got something out of it. Hopefully I was able to keep you awake. Yes, the recording should be made available. Basically, what I'm going to be doing here is Brandon. I'm going to be handing it over to him, and thank you. He has a little bit there to finish everything up for you on that. So, any questions? Any questions? Yes, basically, I do have some handouts here. Let me go and upload these here. These are kind of after class type things. And first, it's called Basic IP Concepts. And then I'll upload the answer key, right? So again, it's just a collection of more questions that we just had. And but no cheating. There's the answer key. And we have another one that's called Design an IP Subnet Network, and the answer key for those questions. So these are great little things, after our little meeting here, maybe when you have time, maybe on the weekend, just kind of go through there, read the question, kind of work out the answers and check it out. All right. So Brandon, I guess I shall leave it to you.
Well, thank you so much, John. If everyone can go ahead and put either a thank you in the chat for John, or go ahead and do a reaction and give it a pause, whatever it may be. We just appreciate John so much in all of his efforts in preparing for this webinar and presenting it today. We do want to go ahead and I'll just show this real fast. I wanted to just thank you all for coming today. And as you are leaving, once you exit the Zoom webinar, you will have a 1-question survey pop up on your screen. And it's just simply asking, would you like to continue the conversation? What that means is if you are interested in learning more about New Horizons, how we can support you in your learning development and your company's needs, all of that, we are more than happy to get you connected with the right people to be able to have those discussions. So if you are interested, go ahead and press yes on that question. I also would love to invite you to follow us on LinkedIn, join us for more webinars in the future, join us in class maybe. And also lastly, I do want to just specifically address that question around the recording. So the recording will become available on our website within a couple weeks of the webinar, both our website on the library and also YouTube. So just keep an eye out for it. It's typically there within a couple weeks. So, but if there are no other questions, we thank you all so much for coming today and have a wonderful rest of your day.